So here comes a picture for a cardiovascular system as an example. So very important function of a number of our organs and organ systems is in fact transport of molecules that require for our growth and nutrition and repair mechanism and communication within the body, such as hormonal transport. So that such an example is here cardiovascular, and the next page, respiratory system and digestive system and renal system. All these many physiologically important organs are in fact their function is a lot about transporting molecules. So here is respiratory system, which brings oxygen into our cardiovascular system and take off those carbon dioxide and the waste. While the other is a digestive system, you can see that it brings the nutrients into our body through this gut system and through the uptake inside epithelial layers of the gut, and that gets into the liver, and then nutrients can be absorbed. And also renal system is movement of our waste products outside of the body. So these are all like transport of molecules. So that's why understanding transport phenomena is fundamentally important for basic of this. So here, I already talked this one, but I want to review this again because it's such an important topic, tracer balance in the body. So for example, a drug molecule, for example, is ingested in food and passes out of body in the urine. And that phenomena, let's having some simplifying assumption. So first, tracer is unchanged its original form during passes through the body, which means it's neither generated nor consumed by chemical reactions. So let's just assume this. And then there's no more introduction of tracer into our body during the period of observation, which is at time 0 tracer intake, and then over the following times, there's no introduction. And disappearance of tracer, let's assume our body is, secretes this, the output rate is proportional to the amount of the tracers remaining in our body. So in this case, we can assume this as a first order kinetics. And mathematically, this can be described as this, you remember the systems approach, the accumulation on inside the system boundary of the tracer molecule will be increased by this input flux minus output flux plus the net generation, which is generation minus consumption. Let's assume, because we have assumed this as a 0, and there's no more influx right after intake, and there's only outflux, which is proportional to the amount of the mass inside this system boundary, and that's accumulation rate. Just to note that this requires some basic understanding of simple differential equation of first order. So I'm gonna having an example of tracer, different kind of tracer. Let's say then we have to look at over time, it's x-axis, while y-axis is the relative concentration. So we put 3 different kinds of half-life, which means the time from the beginning to become a half of this concentration, that the duration of the time can be 1 minute, 15 minutes, and 180 minutes or 3 hours. So that's, if these graph follows a simple first order kinetics, then it's a good idea to convert this one into a log scale, because the log scale will make it as a linear graph, which simplifies the understanding of this.